Okay, hello guys. We are starting on integration today. So integration is the opposite of differentiation. So differentiation is all about finding the slope of a line. Integration is the opposite of that. And it turns out the opposite of finding the slope of a line is to find the area under it. Wild, I know. So, in coming lessons, I'll explain a bit more why that is the case. But turns out that area under the curve is the opposite of slope of the line. Um, so we're going to be using calculus to solve these puzzles eventually. But before we get to the calculus side of things, so the actual integration, we're going to do this by first principles. And the first way you would try and solve area problems is to do it the old-fashioned way. So what are some ways we could approximate the area under this curve? We could count boxes. We figured out how big each one of these boxes is and say, okay, we've got 1, 2, 3, 4, 5 full boxes, and then we got 1, 2 most boxes, and one sort of a third of a box and one fraction of a box. You can sort of figure out how much area is under the shape there. We could split it into pieces. So you could maybe do a square, and then maybe a triangle. Like, it wouldn't be perfect, but that might approximate it. You could do a methodical, make boxes. So you could do the first box, one box across, then do the next one, and each time I just go across. So if you found the area of each of those boxes, you could add them up, and that would be a pretty good estimation of the area as well. Yeah, that's essentially the method that we're going to end up doing for these approximations. A little bit more fancy than that, but that's essentially it. Okay. So, depending on what error approximation you use, the errors will be different. The best way to ensure a low error is to use more shapes to break up the shape in the estimation. So, we're going to do this doing left and right boxes. We're going to use 4 boxes. I'm actually going to... No, we're not. We're going to use 2 boxes each. I'm going to do the left box method first. And if I draw in my left boxes, all the left box means is that the left of the box is touching the line. Oh my goodness, go away, Autodesk. And then my second left box would be about there. So my total area be box 1 plus box 2. Box 1, looking at it, it is too tall, so length by width. It is too tall and it's 0.5 across. 2 times 0.5. And my second box, it is about 3.2. And it's 0.5 across as well. So that gives us 1 plus 1.6. So my total area is around about 2.6 units squared. We don't have units, so we're just going to say units squared, because I don't know if it's meters, centimeters, whatever. Let's do a right box now. And a right box is the exact opposite of a left box. It just means the right-hand corner of the box is touching the line. So there's my first right box, and there's my second. There we go. So the right box method. Total area will be box 1 plus box 2, length times width plus length times width, and they all have a length. So they all have a width of 0.5. The length of the first box is 3.2 times 0.5 plus. Now my length of this one is 5 times 0.5, so that's 1.6 plus 2.5, 4.1. 4.1 units squared. Now, looking at that, guys, does it ask us something? So, okay, looking at that one, you can see that those answers are pretty far apart. Like, the second answer isn't that far off being double the first answer. So this obviously isn't very accurate. If you wanted to make it a little bit more accurate, you can do what's called the middle box method, which is exactly what it sounds like. It means the middle of the box is touching the line. So you can see that would be, it misses some out, there, but it also adds some on there. So it sort of splits the difference between the left and the right box method. That being said, it's pretty clear in this function that the left box method is leaving a whole lot of unmeasured area. And the right box method is overestimating the area. So this bit that I'm highlighting is overestimated in the right box method. So we don't really, it's not a great method. We really need to account for the fact that they're not really boxes. So that's why we get on to the next method, which is the trapezium rule. So use 4 trapeziums to estimate the area here, and that's our function y equals negative 0.5x squared plus 3x plus 5. So we have 0 to 4, we want 4 boxes, and we're going to do a trapezium, so my trapezium is going to look like this. Okay, my second trapezium will look like this. Straight away, you can see that this is way more accurate of an estimation than the previous one. Okay, now, you might be sitting there and thinking, but Mr. Parker, it's been a while since you know maths. I don't remember the formula for a trapezium. And that's a good point. The formula is something like this. So the area equals a plus b over 2 times the width, where a is the 2 separate heights. So we're going to have to do some funky math here because, yeah. So trapezium 1, trapezium 2, 3, 4. To find, I hope you can see, this here will be A, that height for trapezium 1. And then that will be B, there. And my width will just be 1. So for trapezium 1, the area will be A plus B over 2 times the width. Now, my width is 1, because 0 to 1. My A, well, that looks like it's like 5-ish. Actually, it will be 5 if you sub in 0 to that rule. I'm not sure what that one is. It's not quite on the line. But what I do know is that if I just figure out what my function f should be using blue. If I figure out what my function f is, at the x value of 0, that will give me my a measurement. And then, oh goodness, I'm starting to like press things on the screen. And if I figure out my function at 1, that will give me my b measurement. Now, I really don't want to be just subbing in and out numbers into that rule there, negative 0.5x squared plus 3x plus 5. Luckily, we live in a time where we can solve f0, f1 in graphics calculator. Okay, so let's do that. So negative 0.5x squared plus 3x plus 5. If I go to my graphics calculator, I go to y equals 2. Let's clear these out because I don't want to have random junk in there. It was negative 0.5x squared. Is that right? Negative 0.5x squared plus 3x plus 5. Plus 3x plus 5. So I've got my formula there, and I'm just going to look at my table values, guys. Makes it way easier. So if I set up my table, I want it to start at 0 and go up in ones. So if I then go to my table, f of 0 is 5, f of 1 is 7.5. So I can put that into my rule, equals... So it was 5 and 7.5. Now, so that ends up being 6.25. Whoops, wrong color. .25 units squared. Okay, I'm running out of a little bit of room there, guys. So I'm going to do the other ones all together. So I'm going to say 2 plus 3 plus 4. Well, that's just going to be this same rule. A plus b over 2 times w. So, but instead of a, for line 2, it's the function evaluated at x equals 1. So that's going to be f1 plus f, and then to get the second height, it'll be the function evaluated at 2 over 2 times width plus, and then for the next one, it's going to be f2 plus the function evaluated at f3 over 2 times w plus, and it's going to be the same thing, f3 plus f4. Over 2 times w. Now, I'm going to once again cheat, guys. I'm going to add in this one because I already calculated that one, plus 6.25. So when we solve this now, let's go back to our graphics calculator. We want f1 and f2. So f1 is 7.5, f2 is 9. 7.5, then 9. 7.5 plus 9 over 2 times by 1 plus, and f2 is 9 plus f3, 9.5 over 2 times 1 plus f3 is 9.5. Can you see that the two different trapeziums are sharing this each point, right? So this point here is shared by trapezium 1 and 2, which is how I'm just saying straight away it's 9.5. And that's going to become important later on when we get our actual rule. So 9.5 plus 9 over 2 times 1, and then plus on triangle 1, trapezium 1, 6.25 as well. So I'm going to really quickly do that in my calculator off to the side here. I won't do it on the screen one just because it'll take a bit longer. 7.5 plus 9 equals over 2. So 8.25 plus, and then I'll be 9.25 plus 9.25 plus 6.25. And I got 33 units squared. Okay. That was a long one, guys. But luckily, we have a general rule for this, where our approximate area is equal to the width of our slices divided by 2. And then you times that by E plus 2M, where E stands for your endpoints. So the sum of the endpoints. And M is all your midpoints. So if I was to look at this one up here, this would be an endpoint, an endpoint, a midpoint, a midpoint, a midpoint. And the reason it's 2 times M is because you can see that we're using this one twice for trapezium 1 and 2. This midpoint gets used for 2 and 3. This one gets used for 3 and 4. So I don't know if you could see my mouse there. Whereas the f of 0 and the f of 4 only get used once each, which is why it's E plus 2M. So your endpoints plus double your midpoints. Okay. We'll do this example together, and then I'm going to get you guys to have a crack. So, calculate the approximate area under the curve, f equals 2x squared plus 3, from 0 to 3 using a width of 0.5. So, our area equals width over 2 e plus 2m. Now, width is given to us, so my area is going to equal 0.5 over 2. And I have to figure out what e and 2m are. So e is going to be the function evaluated. We're going from 0 to 3, so it's going to be those two endpoints. The function evaluated 0 plus the function evaluated at 3. So let's figure that out. Let's chuck our function into the graphics calculator, and we'll use the table once again. So 2x squared plus 3 is our function. So let's go to y equals 2, clear that one away. 2x squared plus 3. Let me just check that's right. 2x squared plus 3. Excellent. And for our table settings this time, we do want it to start in 0, but our width is 0.5. So we're going to go up in 0.5s. And let's go to our table. Our function at 0 is 3, and we're going up to 3. Our function at 3 is 21. So 3 plus 21 equals 24. Now, I just need to find my midpoints. My midpoints will be a bit more annoying because we've got to count up all the midpoints. So that will be my function evaluated at 0.5, at 1, at 1.5, at 2, and at 2.5. If we went one further, we'd get at 3, which is one of our endpoints. So we just got to plug in those numbers. So 0.5, 1, 1.5, 2, 2.5. So 0.5 is 3.5, and then 1 is 5. 3.5 plus 5. So I should be doing that in blue, shouldn't I? So now we need 1.5, 2, and 2.5. 1.5 is 7.5, 11, and then 15.5. 7.5, 11, 15.5. So 11 and then 15.5. Let me just check that. 7.5, 11, 15.5. Yep, that's right. So now we just got to solve that. 3.5 plus 7.5 is 8, 11, 22, 27, 27 plus 15.5 is 42.5. 42.5. So that gives me a final area. I'll just do this in my calculator off to the side again. 0.5 divided by 2, bracket, 24 plus 2 times 42.5, close bracket. I got an estimated area of 27.25 units square. Okay. So guys, these ones aren't too bad. Now that we're not actually having to physically do the areas, we can just put it all through the graphics calculator. These aren't too bad at all. So on the next pages, I have a couple of ones. I want you to solve this problem by using 2, 4, and 10 slices. And then I think there's another one. Yep. This one actually gives you x and fx. It wants you to find the appropriate ones, and then this is the final one that it wants you to do it using the widths that it's giving you. So those 3 questions I want you to do. The reason I'm getting you to do it in the book instead of the textbook is we don't have the textbook doesn't actually have these questions in it, so I've just put them in the workbook itself. So that's it, guys. I will leave you to it. Have a good one. Bye.